David Groves, thank you so much for joining us today. I think one of you referred to him as the grandfather of orogenic gold research. Yes, I'm thrilled that he's with us today with an extensive career, over 500 highly cited published papers, 13 medals and prizes, and many other accomplishments. It's going to be incredible hearing some insights from him today. So he'll be chatting with us about mineral systems, Craton margins, and exploration spaces for diverse mineral deposits. So thank you so much, David. It's absolutely wonderful having you.
Thank you very much, Jess. You should have pointed out that the reason you're not having a comedian is that Rich Goldfarb told you that my whole talk would be a comedy. Largely a comedy. Not
necessary today, yeah.
A comedy of errors, he would think. Okay, so we'll just go ahead and I'll start with a list of topics that I hope to cover. I was very fortunate in my day in University of Tasmania. I think Professor Sam Carey was the most wonderful professor, very innovative and always inspiring. And the two takeaway points I got from him were: disbelieve if you can. Never go into something and believe it. Always disbelieve, and if you came out the other end, believe it. And he always said, you'll never solve a problem unless you look at it at the appropriate scale. And I think most of global problems that we have with politicians and others is really a scale problem. They just can't see it at the right scale. I want to talk briefly about mineral systems. They emphasize critical components like geodynamics, fertility, architecture, and preservation in a logical way. Most economic geology studies are at deposit or increasingly sub-deposit scale because of the technology advances, so they don't really cover most of these parameters. There are some mineral system studies of a particular mineral deposit group, but they're pretty rare. And even less common are studies that link related mineral systems. And even rarer are integrations of mineral deposit groups into geodynamic settings. So we all know that academics want to know how a deposit formed and explorations want to know where it formed. So it's important to see what settings, which settings are most common. And today I want to examine Craton and thick lithosphere margin, not so much thick lithosphere because I don't have Graham Begg's data set and I need that really if I was going to discuss it. So I'm going to be more simplistic and I'm going to talk about them in terms of geodynamics and preservation. I'll explain that in a minute. Because Craton margins are structural sites that control magma ascent and sedimentation. They're sites of metasomatic modification of lithosphere and subcrustal fluid liberation. And in conjunction, these factors lead to an array of contrasting mineral systems located in very similar positions. And of course, this has implications for mineral exploration. So things that aren't normally thought about in economic geology from an academic point of view can be discovered cheek by cheek if we take a slightly different approach. I'll just start off with disbelieve if you can. So effectively, there are probably two groups of people. We can see this, I think, in climate science, climate change, or what was called global warming until we realized there wasn't much global warming. But on the left hand, we've got those that follow the narrative and those that analyze the fact. I just want to read something while I'm here. So if we look at history, minority opinions, the heretics or deniers, are almost consistently correct because the majority of people have been unknowingly indoctrinated. So if we look at some of the statements of the past and examine them, the earth is flat. The sun revolves around the earth. The reds are under every bed, not just the ABCs and BBC's beds. A nuclear holocaust is inevitable during the Cold War. The millennium bug will be catastrophic. anthropogenic climate change will cause catastrophic events never before seen on Earth, or at least in human history. Australia's dams will never be full again. It's laughable here. We had 28 days of solid rain. 24-hour news and social media will improve optimism, knowledge, understanding, and social behaviour. And big data is the solution to all our problems. And I think we can see that most of those, if you'd been a heretic and survived, you'd probably be dead, or a denier in the modern world, you would have been correct and the majority would have been incorrect. So how do we go about getting this wisdom and becoming someone who's a denier who is correct? Well, I think the best way to do it is to either go and look for people who are left field thinkers, or in the slide I'm going to show probably right field thinkers, someone that's thinking out of the centre, and we've got to go and gaze at a crystal ball. So Rich Goldfarb arranged this for me. You can see me on the right-hand side of this photo with my great friends here, gazing into the crystal ball and coming up with something which was quite unusual in politics in this particular case. So what are the critical elements of a mineral system? Well, we've got geodynamics at the bottom. So that's the main tectonic control on where deposits are sitting. We've got fertility. Where does the fluid and the metals come from and how are they deposited? What is the architecture, the sort of plumbing system of a hydrothermal system? And then most importantly, really, and hardly ever mentioned in economic geology, preservation. Will the deposit, if it did form, be preserved? So this has been an Australian promotion, really. It started with Leslie Wyborn from, I think it was probably the Bureau of Mineral Resources in 1994. And then people like Cam McQuaig and John Ronsky are local from here, and I'm proud to say both PhD graduates of the centre that I was running. Frank Bierlein is another person. And in recent times, Dave Houston from GA. So this has been really pushed by Australians. If we look at the literature, however, so I've tried to classify the papers from 3 major economic journals for 2020, and I've put them there. And you can see the red is the thing that is probably the most important, global scale, then province, going down to blue, which is sub-deposit scale. And we can see that 0.75% actually have the words mineral system in the paper, and less than 15%, probably much less, are actually relevant to exploration. So how could I try and look at this system? Well, here's an example of an individual mineral system for orogenic gold that I've just recently published. So we start in geodynamic setting, look through fertility, go up through architecture, and then how they're going to be preserved, because orogenic gold is preserved because of its late orogenic timing. It's the last thing that happens in the terrain, so it's preserved. Some of you who know John Ronsky will see things like transient exits and threshold barriers and so on, which I've unashamedly taken from some of his concepts. But that would be the sort of thing we'd be trying to do to decide on what exactly are the critical parameters of an orogenic gold system, and what can we get out of that, which of those parameters will be useful in exploration. Another view we could take would be to look at these critical elements in another way. Instead of applying them to one system or one or two systems, we could try and look at them in a different context. So what are the things? The thing that's probably the most variable will be fertility. All the stuff that we mostly study, fluid inclusions and crystal inclusions and God knows what, all the technological things relate really to fertility. Architecture's more similar because we always need something to, a fault or a fracture, to move fluid along. The things which are the thing that's most constant really is geodynamic setting. There are only a few geodynamic settings in which deposits form, and the geodynamic setting will determine preservation. So if you're in an uplifting arc, a modern arc, for example, and you're producing porphyries and epithermal systems, chances of preservation in the geological record in the past are very low. If we're sitting on a Craton margin, so I'll explain in a minute, for example, we're looking in a convergent margin setting where we've got convergent margin on a Craton boundary, the chances of preservation are very high because the Craton will preserve them, as I'll show later on. So I've just taken those two parameters and looked at them without having, as I've mentioned before, I don't have all the great data that Graham Begg has got. I can't afford to buy it. So I'm retired. So if we just look at a global map, so the red are the Cratons that we recognize around the world, the Proterozoic terrains, which are in the darker green color. There would be zones within there which were thick lithosphere, which we'd need a lot more data than just the geological data that I've got access to. And then we've got the younger Phanerozoic orogens around. So eventually talking about the red areas here with a little bit of discussion about thick lithosphere where I've got information. Why is this lithosphere important? We can see from this diagram that the thickness and the composition of the lithospheres change with time. So in the Archean, it was much deeper, much bigger. We've got a big keel. So under Western Australia, we've got a 250 kilometre keel. Over in the eastern states, of course, it's much less than that in general. And the Archean lithosphere is more buoyant. It sort of floats on the on the mantle, if you like. So it's harder to destroy. So that's the reason that these Cratons are so important. They're thick, they're buoyant, they're difficult to destroy. They last virtually forever. They're still around even though the oldest crust is in them. And what happens around these Cratons, of course, they're the rigid blocks in the crust, and around them we get rifting, extensional openings. We get mobile belts, which got compressional or belts or transpressional belts, and these will locate around the margin of these Cratons and build sort of bullseyes around them. And if we look what happens around these Craton margins, we can see from the magnetotelluric image of the Darwell Craton there, we've got very, very deep fault structures extending way below the moho, which is the white line, into the deep mantle. The second one shows the North China Craton. We've got zones of lithosphere and a stenospheric uprise around the lithosphere. And then the bottom one, number C, shows the incredible complexity of these margins where you need a whole lot of data, as I've mentioned, Graham Begg has amassed over the years to try and understand exactly what the geometry of these systems are. But we can see they're incredibly complex areas with deep faults. Because convergent margins sit on the edges of Cratons or thick lithosphere, they're the solid block behind the convergent margin. When we get subduction, during subduction, we get dehydration, decarbonation, desulfidation. As the slab goes down, we're releasing fluids that go into, either they might come directly, as I'll suggest later on, or they go into the lithosphere and they metasomatise and fertilise it. So we get enrichment of metal elements when we break down pyrite, for example, which might be in the sediment slab. Pyrite goes to pyrrhotite. Pyrrhotite can't hold all the elements that Ross Large talks about in the pyrite. They all go off. The sulfur goes off because we desulf. FeS2 goes to FeS, and we liberate all those materials and they fertilize the lithosphere underneath or adjacent to the craton. So lots of important processes are going on around these craton margins. And what sort of deposits do we find? So we can subdivide these. So perhaps most obvious one is magmatic deposits derived from this metasomatized mantle lithosphere, things that have got an alkaline affinity in general. We can see I've just listed them there: carbonatite, copper and phosphorus deposits, carbonatite, rare earth, niobium deposits, corona type. I put that in orange because I've got no images. When you try and find cross sections and so on of this, they're all extremely boring for some reason. And just briefly, lamproite associated diamonds. So they're the groups that one would put in this group that would be on these margins. So if we look at Palabora, for example, I can't remember how many industries are set up around there, but certainly there's copper, phosphorus, rare earth elements, vermiculite, sulfur, and so on, all around this one complex. You can see the scale. You can see a kilometre down at the bottom there. This is a massive system with a carbonatite with a phosphorite rim that's containing the copper, and then all these pegmatoidal peroxenites, which contain apatite and various other minerals which are exploited. To me, this should be on the bucket list of every economic geologist. It's a fantastic deposit, and it sits right in Kruger Park. And if you go in the afternoon and visit Palabora, you have to go into a little platform because you can see all the lion's paws outside outside the platform where they've been in the evening. Just showing the open pit, and then below some of the incredible rock types that you see at Palabora, just unbelievable phlogopite diopside, apatite. So the green is either diopside or apatite, carbonatite sitting there. These are just unbelievable alkaline related pegmatoids, basically. And one of the important things here is that this highly mineralized, so copper in a carbonatite is quite rare, but you can see the different trend. There's epsilon neodymium, epsilon strontium diagram there. You can see that world carbonatites, African carbonatites always form an almost vertical array there, that mantle array, but Palabora sits out on the side and has unusual strontium isotopes. You can see lamproites, which I'll briefly mention, have a similar trend. And this thing called ver genoeg, which means far, far away in Afrikaans, it's got a similar trend. It's one of the world's largest fluorite deposit, again, I think with alkaline affinities, because it's a fayalite, hematite, magnetite, fluorite deposit. So extremely unusual. But that trend, I'll show this for Bayan-Obo. Bayan-Obo sits on the edge of the North China Craton. It's obviously the largest rare earth deposit in the world, carbonatite associated. One of the reasons that China dominates the rare earth element market. See the size, you can see 2 kilometre scale. At the bottom below Bayan-Obo town, see this, the horizon that contains these ore bodies is kilometres long. Just an absolutely amazing giant deposit. And again, when we look at the data, we can see the normal mantle trend, and we can see Bayan-Obo coming across into having a more crustal influence on the deposit. So these sort of trends seem to be extremely important in these giant mineralized carbonatite related deposits. And again, we can look at Western Australia, the ARGYLE diamond deposit in a lamproite, not in a kimberlite. So lamproites are forming on the Craton margin where there's a lot more volatile material. Often the diamonds get destroyed or broken down, so ARGYLE produce mainly industrial scale, industrial diamonds because of this. But people believe that because of the higher volatiles, there's a lot more seismic activity in the emplacement of these, and many people think these beautiful pink diamonds that I've shown in the upper inset there are actually related to stress, that these colors are related to not to just trace elements in the diamond, but to stress, and that's why they're so rare, because they're only occurring in this type of deposit, which is occurring on the craton margin instead of in the center of the cratons. We can look at iron oxide copper gold deposits like Olympic Dam, intrusion related gold, all of these occurring on craton margins, Carlin type gold deposits. They're probably not magmatic hydrothermal fluids producing them, but there's a magmatic hydrothermal driver to those systems. So if we look at Olympic Dam, we're sitting on the edge of the Gawler craton. Again, we can see the giant size of these systems. These systems are coming from the lithosphere, or at least the MOHO. They're very high energy systems, so they're giant, deeply derived giant systems. If we look at them, you can see the amount of volatile activity from they're typified by breccia pipes with breccias within breccias within breccias within breccias, an amazing number of different brecciation events, and a model that seems to be now accepted, or should be ultra basic magmas there. That's a mistake of the draftsman. Ultramafic is mineralogy, ultra basic is chemistry. It's a very common mistake. But we've got extension as asthenospheric uprise. We've got melting of a subcontinental lithospheric mantle underneath the craton, producing ultra basic magma, probably lampropheric magma, because we get a lot of lamprified dikes around the edges of these systems. That is so hot it melts the bottom of the crust. We get a hybrid melt. We start to get elements diffusing across that boundary because of the incredible chemical potential gradient. So we got granitic on one side, lamprifier on the other. So we get a mixture of elements migrating across that boundary. And then finally, we get emplacement, either as a magma or magmatic hydrothermal fluid. And at depth, Salobo is in the upper amphibolite fasces, so it's a very deep one. Cristalino and Alamao in Carajás are intermediate, and then Olympic Dam possibly exiting as a Mar, although I know there are other models for Olympic Dam. So we see there, and just recently, well, not so recently, we're seeing these magnetotelluric surveys of the Gawler craton, and we can see OD is Olympic Dam in the top one. We can see the MOHO is about 35 kilometers, is about the bottom of C3. We can see these low recessivity zones below on the craton margin, and these so-called fingers of God, which are pointing up to the deposits from these low recessivity zones. And what I've tried to do down the bottom is to show that this might apply to orogenic gold, for example, which I believe is coming from at least from the MOHO, and in the case of the Chinese deposits, from the metasomatized mantle itself. We can see a whole lot of near vertical, they're somewhat listric at the bottom, vertical magnetotelluric anomalies, which are the big fault zones. Again, being a geologist, I've never believed seismic sections because they always show these faults as listric, but when you've been in the field a lot, you notice that they're vertical in the subgreen schist, green schist, amphibolite, and high amphibolite, they're always vertical or near vertical. You never see them listed, the big ones, not the small structures. And again, if you have a look closely at that, at a bigger screen than me, you can see beneath the Eastern Goldfields superterranes, which is that those fingers are pointing pretty well towards Kalgoorlie. You can see those low resistivity zones at about the Moho level, and some low resistivity zones up those fault zones. So I think these are going to turn out, we're going to find fingers of God in a whole range of deposits that form from these deep surveys, and magnetotelluric surveys are probably the most important geophysical surveys for these these deep deposits, because seismic gives us the wrong impression of the fault positions. I've just shown a schematic section there that shows the schematic relationship of mineral deposits. So, for example, on the Craton, we're seeing bushveld type nickel, copper, PGE, iron oxide, rare earth deposits like Vergenoeg and kimberlites and diamonds. And then on the edges, as we progressively get away towards the margin, iron oxide, copper, gold deposits, carbonatite, rare earth, corona type, iron, phosphorus seems to be a very common element, lamproite, diamond, and so on. So we're seeing a whole range of deposits sitting on those Craton margins because of the metasomatized matte lithosphere. If we look at the intrusion-related gold deposits, both Rich Goldfarb and I think that these are extremely rare. Actually, many things are being misinterpreted as intrusion-related gold deposits. These sit right on the Craton margin, so Fort Knox and so on. It's the only really large one is sitting on that North American Craton. If we came down to the, you can see these are extensional deposits, got these extensional vein arrays. As we come down to the southeast, we come to Carlin along exactly the same boundary. And again, Carlin is sitting on the edges of the Craton, the continental crust. And we can see these trends of Carlin. And when we look in a cross section, we can see the Archean Craton is being faulted down towards the oceanic crust. So it's stepping down. Those steps are controlling where the different sedimentary facies are and controlling where the Carlin type deposits are themselves. All this has been derived by looking at geophysics in also initial strontium isotope ratios and lead isotope ratios. This sort of geometry has been derived. When he was doing his PhD in the Key Centre with us, Chris Wins did some modelling, just trying to put in rigid Cratons. So that's the dark grey in the top one. They're the Cratons being stepped down. They're rigid with some sedimentary layers over them, and just squeezing them about 10%, I think, in this case. What you can see is the faults start to buckle a little bit. You can see extensional faults in a sort of conjugate on the left-hand side, and these anticlinal domes that are appearing. So if they are occurring all the way along those fault, fluid is migrating into the anticlinal high there, and that's why we're seeing the deposits forming these trends or these lines along. So the architecture of the basement is controlling where the sedimentation is and where the deposits is, because, and the linearity. If we look I've just put a cartoon, North American Craton and the trends, Carlin. You can see where the Craton changes its direction, or there's a major fault that the trend of the deposits form. And in the northern part of the Yuyang Basin in China, in that blue area there, particularly, we're seeing young Carlin type deposits. As we come further south, we're seeing older orogenic gold deposits. In my view, anyway in this particular area. So we're seeing them, but these are extremely rare. And again, they're sitting on Craton margins. Can we get hydrothermal deposits derived from this metasomatized lithosphere where we've got no magmatic component? And the answer is almost certainly in the Jiaodong gold province in China. This gold province produces about 35% of all the gold in China from about 0.35% of its surface area. So it's a massive gold province. And I think we see it in other Chinese orogenic gold deposits, although this is more contentious. So my model for orogenic gold is that it occurs deep below the moho from oceanic crust, probably altered oceanic crust, as the isotopes are telling us in a number of places, that are going down the subduction zone. They start off by dewatering, and then at about 500 degrees, they decarbonate. Calcite is no longer stable. Pyrite's no longer stable at about 500. So almost simultaneously, you reduce carbonate-rich fluids and you desulfidize pyrite to pyrrhotite, you release sulfur, and you release all the elements like gold that are carried in these elements. Some modeling at UWA would suggest that the fluid migrates out and ponds about below the moho, which would explain why you can get a whole series of subparallel lithosphere scale shear zones that are mineralized across what is now a craton or an orogenic belt in the younger belts. So here is the top left-hand slide shows where Jiaodong is, that small area on the edge of the North China Craton. The bottom slide shows a whole series of large transpressional fault zones along which are the primary fluid movement, most certainly. And the model that I showed before is probably the model that it must apply here, almost certainly, and from a whole range of isotope evidence now and platinum group element evidence, seems like the fluid didn't directly come off the subduction zone, but it came off from metasomatized mantle that was fertilized by an earlier subduction zone. So again, it's occurring on the Craton margin. Again, it's the biggest gold province in China, and almost certainly hydrothermal, but directly from metasomatized lithosphere. The other China gold deposit, you can see it's very unusual for me. When I saw these maps, very unusual in the sense that many of these orogens are very skinny orogens relatively between the Cratons. So you can see that Qinling, Darby orogens between the North China and the Yangtze Craton. Again, you can see from the red where Jiaodong is, and a whole series of other. And most of these, Huan Xinjiang, West Qingling, Damba, Jiaodong, Aliaoshan belt, growing evidence that these also are derived from metasomatized lithosphere, not from crustal metamorphism, but that is somewhat debatable. So China, to me, is the key to understanding orogenic gold, because if all orogenic gold forms by similar processes, then I think all orogenic gold deposits must form via subduction and or from metasomatized lithosphere. Therefore, they're deep. Therefore, those magnetotelluric structures are the important ones in determining whether you're going to get a major deposit or not, or province. And I've just summarized those, my model as number A, then the China model as B and C, where you've got pre-existing subduction, metasomatizing the mantle, roll back, a centisphere uprise, heating, and then liberation of fluid, which produces deposits in these different settings close to craton margins. There's a slide from Rich Goldfarb. And again, I think you can see here that there are very large deposits, like Murantal is one of the largest, is the largest orogenic gold deposit. These are all significant deposits. Sukhoi Log and Limpiardia are the two potentially largest in Russia. And you can see they're sitting where my professor, Carey, would have called oroclinal bends, where you've got a craton here near Murantal. There we've got a craton covered by sedimentary, so it's coloured in grey. And then up in here, we've got another oroclinal bend around the Siberian craton. These big deposits are occurring near these craton margins, but in oroclinal bends in the zones of most complexity. So I think these patterns, you're seeing these patterns at pretty well all scales. If we look at the map of the Yilgarn Craton, which most of the people from West Australia will be very familiar with, we can see that Kalgoorlie and so on, even the komatiite nickel deposits, are sitting on the edge of what you could call a proto-craton, what was these more westerly terrains, including the Southern Cross terrain there. So it's sitting on a boundary. The most important deposits largely sitting on that proto-cratonic boundary. Perhaps I haven't got or paleocraton margin, if you like. We can look at intrusion-related nickel copper PGE deposits. I've just shown one there at Voisey Bay. You need a lot of complexity, you need channels and so on to catch the dense massive sulfides. But when we look, there were two independent studies really here, one by Wolf Mayer and myself, and one by Graham Begg and his co-authors, both showing that these deposits occur within 100 kilometres of craton margin. You see the big yellow dots there, Duluth, Sudbury, Voisey's Bay. They're the deposits I'm talking about. They're sitting right on the edge of the superior craton. The red ones are things like bushveld complex, Stillwater. They're things occurring in the middle of cratonic areas. We did this all globally, and even though Sudbury is considered to be an impact-related thing, certainly the channeling, it must have been a magma about to produce nickel sulfide, about to be intruded, and it intruded along massive lithosphere scale structures that appear along the edge of these cratons. Even iron ore deposits. These are deposits, of course, where we're dissolving components, we're dissolving silica rather than depositing something. But again, if you have a look at the map, all these deposits are sitting around domes of cratonic material at Mount Wellback, the Brockman, Parapadu, Tom Price deposits, and cloud break along the edge of the Pilbara Craton to the north. These are all bits of the Pilbara Craton that are sticking through the younger belts, and they're controlling where the gold deposits are. And if you look at C, the cross section that's drawn by the Dave Leach group, we're seeing the same sort of geometries we're seeing at Carlin, except in this case, the fluid's being fed from basins elsewhere, going up the fold and back down and leaching the silica and putting it out into the basin. But the geometry is exactly the same. These are occurring. So we're seeing a disparate group of deposits all forming with very similar cross-section, very similar places. The Zambian copper belt type deposits are effectively occurring at a triple point junction between 3 cratons and the thick lithosphere around them in the Paleoproterozoic rocks. So we've got the Kasai Craton or the Congo Craton, Tanzanian Craton, Zimbabwe Craton, and the copper belt, the Philian arc, sitting in the triple point junction of these cratons. You can see they're occurring in fold and thrust belt mainly, or in domal position. They're always structurally controlled. I'm almost certain that they're formed by fluid being moved through the basin during deformation. They're not SEDEX type deposits. So again, they're on Craton margins. Just looking at this map I started with, this is just to show the work that was done by Hoggard et al., where they looked at the thick lithosphere. They looked at this lithosphere that was more than 170 kilometers thick, I think was the figure. And they showed that HYC, Century, Mount Isa, Cannington were all sitting, the big SEDEX deposits were all sitting on the margin of this thick lithosphere, along with Ernest Henry, which is an iron oxide copper gold, of course, and Olympic Dam, Broken Hill, which I think these are extremely unusual deposits that formed in rifts. They're extremely high temperature, low pressure zones, and were all metamorphosed to granulite fascias because of the high heat flow, rather than overthrusting or some other tectonic process. So they're not sitting in that position. When Hoggard et al. In the summary of their buffers, they show for I mean, you wouldn't normally think of SEDEX deposits or MVTs or Zambian type copper belts on and Craton margins. The things don't, well, I haven't seen any literature really that has suggested this clearly before this, but 90% of sedimentary copper deposits, Zambian type copper, in that corridor, 90% of SEDEXs, 75% of MVT, lead. So 85% of global resources in about 35% of continental crust. So perhaps that isn't a big advantage, but to me, it was a result which was unexpected, really. I've just shown a map here which shows some of the most famous deposits. I can't obviously show all the deposits sitting on Craton margins, but I've tried to show the most famous examples of each particular type of deposit or mineral system, we probably should call them, not deposits, that are sitting on these Craton margins. And then if we have a look at some individual terrains, so if we go to the Fennoscandian Shield, for example, very close to these Craton margins, you can see the list there, nickel, copper, PGE. Well, we knew that. This was one of the terrains that Wolf Meyer, he worked in Finland, one of the universities there, Oulu University, so we knew this terrain very well. Chromite deposits, the largest chromite deposit in Europe is at Kemi, which is sitting on that boundary as well. Titanium, vanadium, Karuna type iron ore, which we know, and Outokumpu, this extremely unusual copper zinc deposit with all sorts of other elements in it, again sitting on that margin. And even the VMS deposits tend to sit on those margins, but in this case, they're probably structurally placed along the margins, because when I was a student, I had a look at these deposits like Skellefteå and so on, and I couldn't make sense of them. They were so deformed. Some of them were about 2 or 3 kilometers long and about 3 meters thick or something like this, just linear rods of VMS that had been totally deformed. But that's because they were emplaced, I think, along the Craton margin after they'd formed. And perhaps the most amazing one anywhere is this China example, and to me explains why China is the premier metal and, well, premier producer of many metals and elements because of these craton margins. So on that map there are 66 giant and world-class, I've only put on the giant and world-class deposits, 66 on those craton margins of eastern China. And you can see the diversity. So we've got orogenic gold in Jiaodong, other orogenic gold, antimony, silver, kaolin gold, porphyry skarns, skarn of various types, SEDEXs, MVTs, lead, zinc, silver, hydrothermal deposits, copper, nickel, carbonate associated rare earths, and strata-bound IOCG deposits. And because of these cratons, China, or Tibet in particular, has the oldest epithermal deposits and the oldest major porphyry deposits outside Boddington, because they're protected and preserved by these thick cratons. As you know, the Great Wall of China extends, you can see it from space, and if you extends the entire length of China and beyond, if you take the old fortifications, and the edges of these cratons here are about 75 to 80% as long of the length of the Great Wall of China. So you've got a massive surface there along which to deposit these different mineral systems. If we look at the Yilgarn Craton, where I obviously live, so mineral deposits within 50 kilometres of the Yilgarn Craton, Greenbushes, the giant tin, tantalum, lithium pegmatite, probably what is known now as the largest lithium and highest grade lithium pegmatite resource, probably some Democratic Republic of Congo that might approach it. Boddington, a very contentious deposit. I think it's quite clearly a porphyry deposit based on a whole lot of research, but it's been called partly an orogenic gold deposit, an intrusion-related gold deposit, and so on. But whatever, it's 50 kilometres from the Yilgarn Craton margin. I suspect it's been tectonically in place there. Tropicana, world-class orogenic gold deposit. Nova Bollinger, discovered as a major nickel, copper, cobalt deposit. And now Julimar Gonaville, where there's no resource. I think a resource is about to be released of one small part of it, where I think it has the potential to be the next Norilsk. And until last week, I thought it was the only massive sulfide with similar palladium-platinum ratios to Norilsk, but just by accident, I was looking at something on the northern shore of Lake Superior, and I found that Lac d'Azil, which is perhaps an alkaline intrusion, has high palladium as well. I hadn't picked that one up from the literature before that. So just to, I mean, probably all of you in West Australia know about Julimar and spectacular rise in the share price and capital of the company. Marvelous discovery made from geophysics and geochemistry in a spot only what 30 kilometres from Perth. They're outdated, of course. They've just produced another an August update to this with several more shoots defined. So what's the exploration significance of this? Well, I think there's an exceptional wide range of mineral deposits or mineral systems sitting at these craton margins, making them important exploration search spaces. At a 100 kilometre buffer zone, 10% of the crust captures many deposits. So example, all those deposits in China, the nickel deposits would fit. A 200 kilometre buffer zone captures almost all the relevant deposits. Then a 200-kilometre buffer zone of the margins of thick lithosphere captures 85% of sediment-hosted copper, lead, zinc deposits. Most of the deposits are magnetic. A lot of them contain magnetite. They're conductive. They contain sulfides, or they're heavy. They have gravity anomalies. So these things, although once we've got these corridors, geophysics would be a good tool to find them. I just made a note there, 3 of the most recent discoveries have been about 50 kilometres from the southeast margin of the Yilgarn Craton and 50 kilometres from the western margin of the Yilgarn Craton. And one of the things I think that comes out of this is, if you stop worrying about, I'm going to look at an orogenic gold system, I'm going to look at an MVT system and so on, and you start looking at a more holistic approach, looking at geodynamic environments where there will be preservation, you might find something unexpected. And I think that this applied to Olympic Dam. So Roy Woodall kindly gave me the original slide on which the model was based. So we've got a basement high and a relative basement low. So we have to have a major fault. This could be a crustal scale fault or a lithoscale scale fault. They assumed the copper was coming from basalt. So that would give us, this would give us a gravity and magnetic high on this side and a gravity low, magnetic low on this side because of this fault. So you've got a major lineament, which of course was used in the discovery, and then gravity and magnetic anomalies were used in the discovery. And instead of finding a Zambian copper belt type deposit, which they were looking for, they found Olympic Dam, which was an iron oxide copper gold, the first time anyone had realised one of these existed. And Roy kindly showed me the distribution of the drilling that intersected ore on the scale of Perth, of course, where I live. And you can see how large, anyone who lives here can see how large the deposit footprint is. So I'll leave it there, and thank you for listening to this comedy of errors. And I think if you've got any questions, I think I've finished in reasonable time, given that I was the comedian as well as the speaker. Yes.
You've done well. Thank you so much, David.